Okay, so we have an introduction to nuclear science practice final exam, first year graduate level. So let's begin. So the nuclear binding energy is approximated by the semi-empirical mass formula given here, where delta, forgive my poorly draw delta of A comma C. Z is this for even nuclei, odd A, and odd nuclei. By the way, I'm going to go through this rather quickly so you have this as a reference with the setups and the answers. Here are the constants given for A sub V, A sub S, A sub C, A sub A, A sub P. Part A, derive the condition for the most stable proton number Z for fixed mass number A. So here we go, semi-empirical mass formula nuclear stability problem. So I'm going to go through this quickly. Here's our binding energy. Okay, for fixed A, maximize B with respect to Z. So ignoring the small pairing dependence and using Z times the quantity Z minus 1 is approximately Z squared. We're going to say B of Z is approximately negative A sub C times Z squared over A to the 1/3 minus A sub A, quantity A minus 2Z squared over A. We differentiate dB dz. That's going to give you negative 2A sub CZ over A to the 1/3 plus 4A sub A times A minus 2Z over A. Set it equal to 0. Okay, so each piece here, quantities set equal to 0. Here, here, and here. So our Z stable is 2A sub A times capital A over 4A sub A plus A sub C, A to the 2/3. Or if we divide by that 2A sub A, each term, we get A over 2 plus A sub C over 2A sub A to the 2/3. Okay. So that's for letter A. For letter B, estimate the most stable nucleus for A equals 118. For A equals 118, A to the 2/3 is 24.0, so Z approximates 118 over 2 plus 0.714 over 46.4 times 24.0, so Z approximates to 49.8. So the most stable Z is about 50, and this corresponds to 10. Okay, so moving along, continued for number 1. Okay, so, whoops, sorry. Sorry about that. Letter C. Let's see, letter C, calculate the approximate binding energy per nucleon. So continue, the binding energy per nucleon is estimated by substituting A equals 118 and Z is 50. Substitute into the equation. Okay. And since this is even, our delta equals 1.1 MeV. Numerically, our B is equivalent to 9.88 MeV. Okay, so let's see here. Our B over A, that's approximates that 988 over 118. And we get 8.37 MeV per nucleon. Okay, and letter D, calculate the approximate binding energy, discuss limitations of the semi-empirical mass formula. Okay, the SEMF, semi-empirical mass formula, works well for broad trends but fails near magic numbers, light nuclei, and nuclei with strong shell or deformation effects. That's more of a textbook notes type answer. Okay, moving along to number 2. Okay, so number 2, nuclear shell model. Okay, letter A, explain the importance of spin-orbit coupling in the nuclear shell model. Letter A rather. Nuclear shell model, spin-orbit coupling splits levels with the same orbital angular momentum into J equals angular momentum, that L plus 1/2, and J is L minus 1/2. In nuclei, this splitting is so strong and rearranges the order of energy levels. This explains magic numbers such as 2, 8, 20, 28, 50, 82, and 126. Okay, part B. Determine the ground state spin or I'm sorry, determine the ground state spin and parity for a nucleus with 29 protons, 34 neutrons. So letter B here for 29 protons and 34 neutrons. Proton number Z equals 29 is 1 proton above the closed shell, Z equals 28. The next proton occupies this orbital, and thus the unpaired proton gives this for our J pi, J superscript pi, okay, equals 3/2 minus. Because our p orbitals have this L equals 1, so the parity is going to come out to -1. So, letter C, explain why the magic numbers 2, 8, 20, 28, 50, 82, 126 indicate shell closures. Okay, so the neutron number n equals 34 is even, so the neutrons are paired and contribute approximately 0 net angular momentum. Therefore, the ground state spin parity is, that's going to be J superscript pi equals 3/2 minus. So magic numbers indicate filled shells. Filled shells produce especially stable nuclei with higher binding energy, lower deformation, and larger excitation gaps. Part D, why are nuclear magic numbers typically less deformed? Well, near magic numbers, nuclei are less deformed because closed shells are energetically spherical and resistant to collective deformation. Okay, so that's number 2. Moving along to number 3. Okay, number 3. We're given a parent nucleus X decays into daughter nucleus Y, which subsequently decays into stable nucleus Z. We're given these initial conditions, n sub x of 0 is n naught, and n sub y of 0 is 0. Okay, derive expressions for n sub x of t and n sub y of t. Okay, so let's see, here we have our decay equations. D n sub x dt equals negative lambda sub x n sub x, and d n sub y dt equals lambda sub x n sub x minus lambda sub y n sub y. And the parent solution when solving this differential equation is going to be n sub x of t equals n of 0 e to the negative lambda x to the t. Now, substitute into the daughter equation, this d n sub y dt plus lambda sub y n sub y equals lambda sub x n naught e to the negative lambda xt. And now using an integrating factor of e to the lambda yt, we get this n sub y of t equals lambda sub x n naught lambda sub y minus lambda sub x times the quantity e to the negative lambda xt minus e to the negative lambda yt, assuming that lambda sub y cannot equal lambda sub x. Okay, so what they want us to do is solve the coupled decay equations, define secular equilibrium, differentiate between secular and transient equilibrium. Well, the activity is a sub x equals lambda sub x n sub x, and a sub y equals lambda sub y n sub y. Secular equilibrium, okay, occurs when the parent half-life is much longer than the daughter half-life. Okay, sorry about that. Parent half-life is much longer than the daughter half-life. Okay, sorry about that. Where lambda sub x is much less than lambda sub y. Then, after several daughter half-lives, that a sub y approximates a sub x. And for that t sub 1/2, x equals 9.0 days, and t sub 1/2, y equals 3 hours. The daughter reaches near equilibrium after about 5 daughter half-lives. So 5 times 3.0, 15 hours. Okay, and now to the secular and transient equilibrium. So secular equilibrium is established after 15 to 20 hours. Transient equilibrium occurs when the parent half-life is longer than the daughter's, but not enormously longer. Secular equilibrium occurs when the parent half-life is much longer. Okay, so that takes care of number 3. Pardon me if I went too quickly there with that, but I'm just trying to get through these so you have them as a reference. You can always pause the video. Again, some intermediary steps are not shown. Number 4, alpha decay and quantum tunneling. Explain alpha decay using quantum tunneling arguments. Okay, let me read. B, using the WKB approximation, show qualitatively that the tunneling probability behaves like this. P approximates the exponential of -2 integrated in the integral of kappa of r dr, where kappa of r is forbidden region wave number. Explain the origin of Gn law. Why can alpha emitters possess several discrete alpha energies? Okay, so the alpha decay and tunneling problem. So here, alpha decay occurs because an alpha particle exists as a cluster inside the nucleus and can quantum tunnel through the Coulomb barrier. Inside the nucleus, the alpha particle is bound. Outside the nuclear radius r, the potential is approximately this V of r. Okay, should look familiar. Forbidden region is where V of r is greater than E sub alpha. The tunneling probability, the WKB tunneling probability is this. Okay, it's this, bounded from r to lowercase r sub 2, where kappa of r equals square root of 2m sub alpha times the quantity V of r minus E sub alpha over h bar. And R2 is the outer turning point where V of r sub 2 is equal to E sub alpha. Because tunneling probability depends exponentially on the integral, small changes on E sub alpha cause huge changes in half-life. The decay constant is approximately lambda minus Fp, where F is the assault frequency. The half-life is T sub 1/2 equals ln2 over lambda. Therefore, T sub 1/2 is proportional to 1 over P. Okay, so that takes care of that first page. We just have to add on, do C and D. Whoops. Okay, doing C and D here. Okay. All right. So, right here for 4, right here, Gn law follows because higher alpha energies lowers the effective barrier width, increasing tunnel probability and decreasing half-life. Okay, multiple alpha energies occur when the daughter nucleus is left in different excited states. Each transition has different Q value, so the alpha particle receives a different kinetic energy. Okay, so that takes care of number 4. That was C and D there. And now let's move along to number 5. Okay, so number 5. Whoops. Sorry about that. Okay, number 5. A gamma ray passes through a shielding material. Derive the attenuation law. I of x equals I naught times e to the negative mu x. Okay, so A, interaction of radiation with matter. So we have a separable differential equation. So for a narrow beam, the loss of intensity through the thickness dx is proportional to the current intensity. So di equals negative mu I dx. Okay, and then we're going to do, we're going to treat this as a separable differential equation. This is di over I equals negative mu dx. Integrating ln I equals negative mu x plus c. Using I of 0 as I naught, I of x becomes I naught e to the negative mu x. Okay, B, calculate the thickness here required to reduce intensity to 0.1%. So to reduce to this percentage, we take I over I naught, we get 0.001. Set it equal to e to the negative mu x. Solving for x, ln x equals ln that 1000 over mu, with mu is equal to 0.62 per centimeter, and x is going to be 6.908 divided by 0.62, approximately 11.1 centimeters. So the required thickness here is 11.1 centimeters. Okay, C. Discuss photoelectric absorption, Compton scattering, and pair production. Okay, photoelectric absorption dominates at low gamma energies and high atomic number Z. The photon is fully absorbed and ejects an electron. Compton scattering dominates at intermediate energies. The photon scatters from an electron and loses part of its energy. Pair production dominates above 1.022 MeV, especially with high Z materials. Photon converts into an electron-positron pair near a nucleus. It's more of standard canonical answer. Letter D, explain neutron shielding design considerations. Okay, neutron shielding is different because neutrons are uncharged. Hydrogen-rich materials slow neutrons effectively, while absorbers such as boron and cadmium capture thermal neutrons. High Z materials may be used for gamma shielding from capture radiation. Okay, so that's number 5. Let's move along to number 6. Okay, and this is also canonical. Charge particle stopping power problem. Letter A, explain the physical origin of the Bragg peak. Okay, so charged particle stopping power problem. Charged particles, letter A, lose energy, mainly by ionizing and exciting atoms. The stopping power is negative dE dx. That derivative for heavy charged particles. The beta formula roughly gives negative dE dx proportional to z squared over v squared. Okay, that's for the beta formula. Okay, where z is projectile charge and v is speed. As the particle slows down, v decreases, so stopping power increases. This causes the Bragg peak near the end of the particle's range. Okay, letter B, describe why stopping power approximately scales d dx proportional to z squared, where z is projectile charge. Okay, so the z squared dependence arises because the Coulomb force from the projectile scales with z, and energy transfer scales with the square of the interaction strength. Okay, letter C, compare stopping behavior for protons, alpha particles, and electrons. Okay, for alpha particles equals 2, so stopping power is roughly 4 times larger than for protons at the same speed. Alpha particles therefore have shorter ranges and more intense ionization. Electrons behave differently because they are light, undergo strong scattering, and radiate Bremsstrahlung more readily. Their tracks are less straight and do not show the same sharp Bragg peak as heavy charged particles. Okay, and letter D, discuss relativistic corrections of stopping power. Okay, so for letter D here, we have at high energies, relativistic corrections become important because the particle velocity approaches c. Time dilation changes interaction dynamics, and density effect corrections reduce long-range polarization effects. Okay, so that's for number 6. Let's move along to number 7. And a lot of this is canonical, standard stuff. Very important though. Okay, 7. And I'm going to read A, B, C, and D, and then it all encompasses here. Okay, for number 7, compare gas proportional counters, scintillation detectors, semiconductor detectors. Okay, and let's see what we have here. Describe the signal formation mechanisms, compare their energy resolution. Explain why high purity germanium detector here outperform what we have here, the thallium doped sodium iodide scintillation detector spectroscopically. So, nuclear detectors problem. We're also going to discuss cryogenic detector operation. So, nuclear detectors, so we have all of this. Gas proportional counters detect radiation by ionization in gas. And radiation creates electron-ion pairs. An electron field accelerates, causing gas multiplication near the anode wire. The output pulse is proportional to deposited energy over a useful voltage range. Scintillation detectors use materials that emit light when excited by radiation. Okay, the light is collected by a photomultiplier tube, okay, or photo diode and converted into an electrical signal. Semiconductor detectors form electron hole pairs in a crystal. Okay, so we're up here. And applied electric field collects the charges. The signal is proportional to energy deposited. Semiconductor detectors have superior energy resolution because the energy required to create an electron hole pair is small, typically a few eV, compared with tens of eV for gas ionization and much larger statistical fluctuations in scintillators. Okay, so now we have this thallium-doped sodium iodide scintillator detector. Has high detection efficiency but poor resolution because scintillation light production has larger fluctuations. And then we have the high purity germanium detector. Has excellent resolution because it directly collects charge carriers with much smaller statistical fluctuations. However, the high purity germanium detector usually requires cryogenic cooling to reduce thermal noise. Cryogenic operation reduces leakage current and electronic noise, improving resolution. The drawback is increased cost, complexity, and maintenance. So that's number 7. Very much canonical stuff for that one. And much of this is okay, standard. 7, and now number 8. Okay, number 8, this is a neutron moderation problem. So explain for part A neutron moderation physics. Okay, this is, of course, this is going to be condensed. Neutron moderation. Fission for part A. Fission neutrons are born fast, typically around 2 MeV. Moderation slows neurons by elastic scattering from nuclei. For a neutron, scattering elastically from a nucleus of mass number. Okay. Sorry about the way I read that. My apologies. For letter B, derive the logarithmic energy decrement per collision. So A, the average logarithmic energy decrement is here. The xi equals 1 plus alpha ln alpha minus over 1 minus alpha, where alpha is the quantity a minus 1 over a plus 1 squared. For hydrogen, a equals 1, so alpha equals 0, and neutron energy loss per collision is very efficient. Okay, letter C. Why are light nuclei efficient moderators? So light nuclei are good moderators because a neutron loses the largest fraction of energy when colliding with a particle of comparable mass. Letter D, compare graphite, heavy water, ordinary water. Okay, D, ordinary water is an excellent moderator but absorbs more neutrons than heavy water. Heavy water moderates well and has very low neutron absorption, making it excellent for neutron economy. Graphite has low absorption and good moderating ability, but more collisions are required than in water. Part E, discuss neutron absorption effects in reactor design. Absorption matters because excessive neutron capture reduces the number of neutrons available to sustain the chain reaction. Okay. And more canonical stuff. That's number 8. Let's go into number 9. Okay. All right. Sorry, just getting this in focus. Okay. Sorry about that. Number 9, particle accelerators. Okay, part A, explain the operating principles of linear accelerators, cyclotrons, and synchrotrons. So particle accelerator problem. Part A, a linear accelerator accelerates charged particles through a sequence of RF cavities. The electric field is timed so particles receive energy kicks as they pass through gaps. Okay, moving along here with the cyclotrons. A cyclotron uses a constant magnetic field and alternating electric fields. Particles spiral outward. As their energy increases, the cyclotron frequency is given here. as QB over M. Classically, this frequency is independent of speed. However, relativistically, as M goes to gamma M, so the frequency becomes the following QB over gamma M. As gamma increases, the particle falls out of phase with the RF field. Therefore, ordinary cyclotrons fail at relativistic energies. Letter C, why are synchrotron radiation losses smaller for protons than electrons? Okay, so we could say here, synchrotron keeps particles in a fixed radius orbit by increasing the magnetic field as momentum increases. RF cavities accelerate particles and focusing magnets control the beam. Synchrotron radiation losses scale strongly with acceleration, inversely with mass. Since protons are much heavier than electrons, synchrotron radiation is far smaller. Okay, let's see here. Letter D, discuss beam focusing and phase stability. Beam focusing keeps particles confined transversely. Phase stability keeps particles synchronized with accelerating fields. Part E, explain advantages of collider experiments over fixed target systems. So here, colliders are more efficient than fixed target experiments because both beams contribute to the center of mass energy. In a fixed target experiment, much energy goes into motion of the center of mass. Okay, so that's number 9, canonical. On to number 10. Also, standard canonical stuff. Okay, nuclear fission. Part A, using the liquid drop model, explain fission energetics. So these are also condensed answers. A nuclear fission problem. In the liquid drop model, a nucleus behaves like a charged liquid drop. Surface tension favors a compact spherical shape, while Coulomb repulsion between protons favors deformation and breakup. Part B, discuss neutron-induced fission. For very heavy nuclei, Coulomb repulsion becomes large enough that deformation can lead to fission. Neutron-induced fission occurs when a nucleus absorbs a neutron, forming an excited compound nucleus. If the excitation energy exceeds the fission barrier, the nucleus splits. A chain reaction is sustained when each fission event produces, on average, at least one neutron that causes another fission. Okay, and now moving along, for letter D, that K sub EFF, neutrons in one generation equals neutrons in one generation divided by the neutrons in the previous generation. And if K sub EFF is less than 1, the system is subcritical. If it equals 1, the system is critical, and if it's greater than 1, the system is supercritical. Okay, again, that's standard, canonical. Letter E, explain delayed neutrons and their importance. Letter E, delayed neutrons are emitted after beta decay of fission fragments. They're only a small fraction of neutrons, but they greatly increase reactor response time, making controlled operation possible. Without delayed neutrons, reactor control would be extremely difficult because prompt neutron lifetimes are very short. Okay, that's number 10, nuclear fission. Number 11 is going to be nuclear fusion. Again, canonical stuff. Okay, nuclear fusion, number 11. A, explain why fusion requires extremely high temperatures. So nuclear fusion, letter A, fusion requires extremely high temperatures because positively charged nuclei repel each other through the Coulomb force. For deuterium tritium fusion, we get this. Okay, letter B, this should look familiar. Letter B, discuss the Coulomb barrier. The Coulomb barrier prevents classical fusion at low energies. At high temperatures, nuclei have enough kinetic energy and tunneling probability to fuse. Letter C, state and explain the Lawson criterion. The Lawson criterion here gives, this is letter C, gives the approximate condition for net fusion power, that N, T, and then T sub T, NT tau E, right here. And this must be sufficiently large where N equals the plasma density, T equals the temperature, and the tau sub E, energy confinement time. Okay. All right, and pardon me if I mispronounced that. Went pretty fast. Letter D, compare magnetic confinement fusion, inertial confinement fusion. Part D, magnetic confinement uses magnetic fields to confine a hot plasma for relatively long times to at moderate density. Inertial confinement compresses a fuel pellet to extremely high density for a very short time. Here, E, discuss major engineering obstacles to commercial fusion. For letter E, major obstacles include plasma instabilities, neutron damage, tritium braiding, heat exhaust, materials degradation, plasma confinement, and economic power extraction. Okay, so that's number 11. Pardon me if I mispronounce anything. Number 12. Okay, again, these are very canonical. Number 12, collective nuclear models distinguish between single particle motion, collective motion. That's letter A, collective nuclear models. Problem letter A, single particle motion treats nucleons as moving independently in an average potential. Collective describes many nucleons moving coherently, producing vibrations or rotations of the entire nucleus. B, describe rotational and vibrational spectra. For part B, a rotational spectrum has energies approximately this: E sub j, h bar squared over 2I times j times the quantity j plus 1. Okay, where I is the moment of inertia, this implies the nucleus is deformed and can rotate collectively. A vibrational spectrum has nearly equally spaced energy levels similar to a quantum oscillator. Okay, and let's see. Okay, so that was letter C. Okay, all right. Letter D, explain quadrupole moments in nuclear deformation. Quadrupole deformation describes deviation from spherical symmetry. A non-zero quadrupole moment indicates an elongated or flattened charge distribution. Okay, letter E. Let's see here. Explain how collective and shell models complement one another. Collective and shell models complement each other because shell models explain single particle structure in magic numbers, while collective models explain deformation and rotations and vibrations. So that's number 12. Again, that's canonical. 13, moving along. This is also standard. Whoops. Sorry about that. Whoops. Sorry about that. Okay. 13, radiation dosimetry. Letter A, define absorbed dose, equivalent dose, effective dose. Okay, so radiation dosimetry problem. So absorbed dose is energy deposit per unit mass. D equals E over M. Its unit is the gray. Given here. Equivalent dose accounts for radiation type. H equals dQ, where Q is the quality factor. And then we have effective dose accounts for tissue sensitivity. E equals this sigma, and then you have T, and then you have that W sub T, H sub T. Okay, the weighted tissue. Okay, and letter B, why is alpha radiation highly dangerous internally? Alpha radiation is dangerous internally because alpha particles have high ionization density and high linear energy transfer. They deposit large energy over short distances. Externally, alpha particles are usually stopped by skin or paper. Part C, determines stochastic and deterministic effects. Stochastic effects are probabilistic, such as cancer risk. No strict threshold is assumed. But as a note, who knows what AI is going to find out in the next decade or so, or within. Deterministic effects have thresholds and become more severe with increasing dose, such as burns or radiation sickness. D, compute equivalent dose using H equals dQ, where H is equivalent dose, D is absorbed dose, Q equals the quality factor. For the dose calculation, okay, if we have a gamma, D gamma equals 0.8 GY, and then Q gamma equals 1, H sub gamma equals 0.8 times 1. That's 0.8 M. SV. Alpha, D sub alpha equals 0.03 m. G sub y. Q sub alpha equals 20. H sub alpha is 0.03 times 20. That gives us 0.6 MSV. Total equivalent dose would be 0.8 plus 0.6, so 1.4 MSV. Okay, and explain the ALARA principle. ALARA means as low as reasonably achievable. It means radiation exposure should be minimized using time, distance, and shielding even when below legal limits. Okay, and let's move along. 14. Okay, 14, reactor physics. Part A, define the effective multiplication factor for K sub EFF equals neutron production over neutron losses. So reactor physics, and I'm just going to read these. Explain the four-factor formula qualitatively. That's for B. For C, discuss moderators, control rods, reflectors, and coolant systems. Explain the xenon-135 poisoning, and explain prompt criticality. Okay, so the effective multiplication factor, that's going to be equal to neutrons K sub EFF equals neutrons produced in one generation over neutrons lost in the previous generation. The four-factor formula is this K sub infinity equals eta, this whole piece here, where eta equals the neutrons produced per thermal absorption. In the fuel, F equals a thermal utilization factor. And then we have the resonance escape probability here and the fast fission factor here. Okay. For a finite reactor, K sub EFF equals this K sub infinity P sub NL, where P sub NL is the non-leakage probability and the moderators slow neurons. Control rods absorb neutrons. Reflectors reduce neutron leakage. Coulomb remove heat. I'm just going in order of these. Xenon-135 is important because it has an extremely large neutron absorption cross-section. Okay, and over here, it is produced from fission products and can suppress reactor power after shutdown or power changes. Prompt criticality occurs when the reactor is critical using prompt neutrons alone without needing delayed neutrons. This is dangerous because the power can rise extremely rapidly. Okay, and our last one for this introduction to nuclear science practice final. Okay, and this is canonical as well. Okay, so advanced reactor systems. An advanced reactor design includes thorium breeding, molten salt cooling, passive safety systems, fast neutron spectrum. Analyze the following. A, advantages of fast spectrum reactor operation. So this is standard for advanced reactor systems. For a fast spectrum. So for A fast spectrum reactor uses high energy neutrons rather than thermal neurons. Advantages include improved breeding, better use of heavy actinides, and potential reduction of long-lived waste. Okay, and my apologies if I mispronounce neutrons or misspelled. Sorry about that. Thorium breeding mechanisms. Thorium breeding uses the following, and here are the reactions here. You can see from here to here, and then the fissile product becomes that. Okay, so part C, safety advantages of molten salt systems. Okay, molten salt systems may offer passive safety benefits because fuel can be liquid, operate at low pressure, and potentially drain into passively cooled tanks during overheating. Sorry about that. And my apologies if I mispronounced anything. Letter D, materials and engineering challenges. Materials challenges include corrosion, radiation damage, salt chemistry control, neutron embrittlement, tritium management, and high temperature structural integrity. Letter E, waste management and proliferation concerns. Waste advantages may include better fuel utilization and reduced transuranic inventory. However, fission products still require management. Proliferation concerns arise because bred fissile isotopes here, such as U-233, requires safeguards. Okay, here, letter F, commercial feasibility over the next several decades. Okay, so F here, commercial feasibility depends on economics, licensing, materials qualification, reliability, safety demonstration, and fuel cycle infrastructure, and also in general government regulations. These systems are promising, but difficult to deploy widely without major engineering and regulatory progress. So that basically is mentioned here. My apologies if I mispronounced anything or misspelled anything, but this is some extra practice if you're getting ready for an introduction to nuclear science exam, and hope this helps a little bit. And thank you very much, and have a great day.